Okay, so welcome to your third lecture of Intro to GIS. Today we're going to be talking about GIS data models. I'm hopefully going to keep this short and sweet today, but we have quite a bit of information to cover, so I'm going to move right into it. So before I get started, what we talked about last time was essentially coordinate systems. Everything you're going to see here has already assumed that coordinate systems are in place, and so the reference system for where the location of this data is already in place. And now we're going to really talk about what the components of geographic data are and really the types. And we'll probably end there today. So the components of geographic data really account for three things, and then technically there's a fourth, but as I mentioned before, there's some problems there. So to start off with, those major three are your spatial locations, where something is happening, the attributes of what is happening, and then the topology, or in other words, the relationship of other variables, attributes, or a continuation of some form of that. And I know that's kind of a confusing term. I'm hoping that I can make that a little bit more clear as we get through this lecture today. It's kind of a gray area. Really, the best thing to think about when you're thinking about topology is the relationship between different variables. And then obviously this fourth example here is going to be time. As I mentioned before, I believe in our first lecture, time is technically something that can be considered as a component of geographic data. It's just very hard to represent when you are working with space as well as time, because you're kind of working in opposite directions with this types of data. So what you end up having is more of a really, I can't call it anything else but like a slider. So you have a snapshots in time, or you have frames of time that are then showing some sort of spatial distribution. It's really not something you can easily show just time and not really consider space in a GIS. It's not really what it's built for. So components of spatial locations. Basically, right off the top, it's got to have a reference system, and it needs to be a point or a line or some sort of feature that is associated with some sort of reference in that common coordinate system. And the spatial features can be represented as a number of different things. They are mainly considered points, lines, polygons, technically volumes, and grids kind of use a combination of these basic classes to create a fifth example. For the point of archaeologists, we'll rarely be using volumes as we're more interested in distribution of things, but in a sense, you could consider volume per se if you were trying to consider the volume of a room or the volume of a vasca or something like that, volume of a cave, something like that. But I think more often than not, you'll find that we tend to fall in line with those first three of points, lines, and polygons. So when we're thinking about these spatial locations that are all happening at point X, the point of having a GIS is to basically see some sort of attribute or something that's happening at X and then have a measurement of it. And so these are referred to as attributes. And attributes can be ordered in some sort of way. Usually, well, not usually, they always fall under four different types. So your qualitative, so your descriptive type of idea is always your nominal. So grasses, trees, buildings, Roman, Etruscan, road, whatever you name it, highway, that's a nominal description. The ordinal is the rankable quality, high, medium, low, single lane, double lane, highway. That, in a sense, is also going to be ordinal, assuming that you're able to explain the ranking within a secondary file. The interval is quantitative, so it's a description of something like temperature or total amount of pottery in an area, total number of trenches, test pits, you name it. It's quantitative, but it's not a ratio, and ratio is your absolute quantities. So it's the total percentage of a pot in an area, or it's pi, or it could be anything. It's just your absolute quantity. So as I got into this, when we're talking about components, topology is one of those, right? And so when you're working with spatial data, the relationships between geographic features are important. It may not be something you're always considering at the forefront of your mind, but it's always something that is shaping how you construct a hypothesis, how you construct a theory, how you construct an idea of how things are related to each other. And there's really no way we can get away from this idea, as it's in a lot of ways, it's how we construct our own environment and how we see everything around us, right? And so these spatial relationships consist of things like adjacency, containment, connectivity, and really just relationships to X to Y, really. And then still, time is considered as part of this attribute, particularly with ArcGIS. It is actually considered an attribute of a feature. So um, time of X. So a coin found here related to this period. When you represent this coin, you're going to actually end up representing the time stamp of that coin as an attribute. And so if you were to map an archaeological site according to the coins that are found within it, and you're trying to show the growth of it, that slider in which you're showing the relationship of time is actually going to be an attribute in each class feature. That may not be my best example yet, but I'm hoping I can clarify it. Topology is kind of a gray, slippery discussion. So let's get into your data views. So there's object view and there's field view. So object view is let's talk about what objects are. So objects are discrete or something with identifiable boundaries. So an archaeological site is a object, whereas fields are continuous and their attributes can vary across the field, right? So elevation is a field, or watershed is a field, right? It's going to change with those attributes. Those attributes are going to change depending on where you are in that field. Whereas an archaeological site is a very discrete boundary. It's going to have essentially you can draw a line around it, and there's going to be a boundary. And there also are attributes to both, but with objects, those attributes are set in stone, whereas fields, those attributes change depending on where you are. So to get into this idea of what we're talking about here with, if I can show, object versus field in a picture. So you have three fields here, right? So your bottom two are fields in a sense, right? So you have essentially just a lush grassy area that I got off of Google that's showing the location of a field, right? It's continuous. So in there, that elevation is going to change and the field is going to vary. The area in which you're measuring land use is also going to be different, right? In the lower photograph of the University at Buffalo's Ellicott campus, all of that land use is going to change different depending on where you are and what you're looking at. If you look at the top, which is just a random person, I looked up AT, so on the Appalachian Trail, that is a fixed point. So the location of that measurement is from a fixed point, and therefore all the attributes are set in stone. The viewing position is set in stone. That in itself becomes an object, right? That person is an object, and it is creating a very fixed, defined area around in the landscape. Okay, so we've discussed all of these ideas and the abstract and kind of discussed them as ideas rather than putting them on the ground, and that makes it very hard to comprehend. Now let's kind of move into the data model, or the way we structure or think about these attributes and components of geographic data, and hopefully it will become a little bit more clear. So with a GIS, there are two types of data models that can be used. Vector data, which is on the left, and raster data, which is on the right. Vector data, wow, did you hear that Buffalo accent? Oh my God. Oof. Can you tell I spent too much time in this city? Vector data consists of three basic representations of data. It is points, lines, and polygons, or in this case, areas. And you can see that on the left that a point is obviously just represented as a single dot. A line is a connection of points, and there can be multiple points. Technically, if you're thinking about this in a very philosophical or theoretical point, I guess is the best way to say it, there are an endless amount of points on a line. So what that means is that you could essentially take any endless amount of points and connect them in a different way or in a different measurement on a line, as long as the two endpoints are the same. And then the final is obviously your polygon, which is a connection of multiple points in a closed area. So all of that is very easily depicted in vector, as you can see from the bottom left. It's very simple, and it looks almost like it's hand-drawn, or at least connected through some sort of computer program. Whereas raster data is not as easily shown. In many cases, it's very easy to do analytics over raster data than it is compared to vector data, but raster data can also show the same thing. So raster data is essentially a cell matrix. So each square is a cell, and they're all interconnected within this matrix, and they can all represent the same type of data in the same way that vector would, but in a more of a boxy way, I guess is the basic way to say it, right? So you have your points, which are single cells, your lines, which are a connection of cells into a single entity, and then there are areas that are essentially just blacked out, or in this case blacked out, or color coded, or including, and they're all enclosed within a certain area. And they all can do the same thing. They all just have their own unique and disadvantages and advantages depending on what you're trying to measure. Okay, so let's go into kind of explaining what we're talking about when we're talking about data models. So your first is obviously vector here. So every position has a pair of coordinates, and that's the same for any type of data model, right? So raster or vector, there's always, every position is going to have a set of coordinates. So if we're looking at this x, y, you can see that all of these points that create either the lines or the polygons, they all have a unique location. So if we take the spline in the middle, or the 3-point line, each of those locations is defined and then connected by a line. And along those lines, there's an infinite amount of points that create this long connection. And lines and polygons are constructed by connecting a series of these points. Points are definitive area locations in space, and they are used to represent geographic features. So points can be really anything. Same with lines. It all depends on what you're trying to represent. So in our case, this is point data of archaeological sites. Without giving a whole lot of information away, this is 415 archaeological sites in Western New York. They are represented simply as points. If you were to zoom in on these locations, they are not going to flush out into anything more. They are simply single discrete points in space that have attributes attached to them. You can also represent the same type of data with a polygon. So in this case, we're looking at an archaeological site in Italy, where each of the discrete units on an archaeological site have been outlined, and they all contain attributes depending on what they are made of, what period they're from, what type of soil could be there, the connections, the overarching layers or the underlying layers, all of that can be considered. To get an idea of what we're talking about here with these attributes, this is really a great example. So this is done in ArcMap, a much older ArcMap than what you'll be using in this class. However, it still remains the same, right? So all of what you see here is essentially an outlining of hydrological data of New York State. All of these outlines are HUC units, or hydrological unit codes, and they're all discrete units where they all kind of stem from different water sources. And as you can see here in this overlying window, each of these polygons have distinct attributes attached to them. So without going into huge description, every polygon, every cell, every single piece of geographic data that goes into a GIS is going to have what's called an FID, or a field ID. So it's an ID number, right? So it marks every single unique unit. I don't really know how else to describe it. Every single unique example that is done in a GIS. When it becomes more and more complicated, each of these are assigned a value. The shape is obviously telling you what type of model, I guess, is a really good way of just giving what type of object this unique entity is. And then there's name associated in this one. There's area that's showing the total area of an area. It's also showing the types of units in terms of water, and that's the MinHuc and the MinHuc 250, which is all description of different types of water at a different level. Anyway, the whole point of this example is really to show how something is basically entered into a GIS and how it holds different unit values. And so at a base level, this is the attributes assigned to each polygon. Okay, with vector out of the way, let's talk about raster, which is in some ways a little bit simpler. In other ways, it has its own problems, it's just like vector. So a raster is essentially a cell matrix. Each of these cells is a defined square in which they can be any variable size or extent, and they consist of positions that are defined by column and rows. So where in your vector data that you had an XY coordinate, it works the same way, except in a raster data set, it is a continuous coverage, and the positions are defined by the column number and the row number, so you have an exact unit. And each cell obviously has a single value. And this comes from whatever value of an attribute you're trying to recognize, right? So you can have raster for hydrological data, right? So it's going to measure some sort of attribute related to water. Or, and oftentimes, elevation data comes in raster because it's a single measurement of elevation data. So the height of elevation is measured as a single number, and it is going to be measured and placed into each cell. And so you have a single number within a raster cell to define what you're looking at. So if I were to break open raster data into multiple files, or to really see what's underneath the hood, into WordPad or something like that, that really like allows you to see what you're going to see, it mainly consists of attributes. WordPad is a really underutilized tool in a PC. I mean, it really lets you break open most file types and just see what's actually written there, and without like damaging your computer. It's something that we should consider more often when we're trying to examine tools, but I digress. Anyway, when you open this, you end up with a header file and the data. The data is mainly the values of the attributes, but without the header file, those are just numbers. The header file, which in our case for ArcMap is going to already, for the most part, be built into the data set. But if you were, like I said, if you were to break it apart and look at it, the header file consists of the number of rows in columns, the cell size, so covering how much landmass is each cell covering, 50, 30, 100, 200, how big are these cells, and then the coordinates of the origin. So what is the 0, cell location, right? And the coordinates of those locations, or that location, I should say, of the origin, can be converted on the fly. You can take the value of the 0, and change it depending on where you have a desire to do it. And mainly what that does is it's a way of allowing you to clip raster down. So when you're dealing with raster data, you tend to be dealing with very large extents of landmass. To give you a great example, I just finished a project in which I was looking at elevation data in Italy. Now, I got a raster data set that covered the extent of Italy and most of Central Europe, and it was considered to be one data set. It was about, I think, 7.5, 7.75 gigabytes. I mean, it was a very, very large file. It took me like an hour to download. I have slow internet, and so some of you may have better internet than I do. But it took a very long time, and to make it actually usable, I had to clip this file down, this roster down, until it was really only covering less than a less than a very small area of Italy. I want to say province, but I know that's not right. Maybe region? It's the Umbrian region? Is that correct? I should look this up. Anyway, it's a very small file, and so what I did when I clipped this file down is I basically changed the origin of the roster dataset. Now, I didn't change the value of the attributes, I simply changed the origin of the roster dataset by clipping it down and basically changing the 0 to 0 from someplace in, I don't know, Germany or France or somewhere like that, Lithuania, I don't really know, down to someplace that was probably within the Umbrian region of Italy. Okay, so on this slide, you actually see three different types of roster cells. On the left is essentially just a random hotspot that you can pull off that shows a single unique point and then the relationship of an attribute moving away and how that measures out. It's more or less a heat map. In the center, you have a subcatchment or water basin that's basically represented in a roster network, and where you have these light blue kind of shaping the volume of water. And then on the left is going to be raw LiDAR data. So there are advantages and disadvantages to both raster and vector datasets. It used to be a much more discrete difference in both of this fight between the two. For a very long time, there were many different GIS systems that really only used one or the other. And much like any other academic discipline, there are fights of which is better. That is now kind of tailed off as computing power has become more powerful. How we use GIS data becomes more important, and thus you have these systems that are able to incorporate both and use multiple data sets of multiple different types and really use them as layering examples. The best example I can give here is that in many cases when you're looking at soils data, so really just geographic information data about soil, that is going to come as a roster data set. So the value of or the type of soil is going to be represented as a code, and that code is going to be represented in each cell, and it's going to have a defined distance. So in most cases, it's between 5 to probably 60 meters in cell size. So each cell represents 60 meters to 5 to 60 meters, let's say. And when you have that, you really have each cell that you're having to look at. But the problem with having soils data is that it tends to be very complex. There's a lot of different types of soils, and therefore there's a lot of different things that need to be rendered onto a screen. More often than not, if you're looking at a large area, computers can still crash when you're trying to load a data set that is that complex. So if you're trying to view soils data and you want to see a very large area, it's often best to convert raster data into vector data because it takes up less computing power. Now, with that long-ranged example off, let's kind of move into what these advantages and disadvantages are. So when we're looking at the advantages and disadvantages of raster, it's straight off the bat, advantages, it's a very simple data model. To get down to the bare bones of it, it's really just an Excel spreadsheet. I mean, that's the best way to think about raster data. It's essentially a matrix. Each of these cells has a unique value, and they can then be represented in terms of whatever color scheme related to the value that they are consisted of. Right? And so the overlay operation can be pretty easily implemented, right? You can kind of overlay it, you can change the value, you can do some sort of function, and it's pretty easy to do a calculation across the entire matrix. It's just matrix algebra at that point. And then high spatial variation is also efficiently represented. So what that means is that when you're showing point data and you're trying to account for attributes values, those attribute values, you often have to go into the actual point or the line or the polygon to see the variation. It is very easy to see the variation of an attribute across the total field in raster because of the change, and each cell is going to have a different color scheme or a different representation depending on the value that is associated with that cell. And so it's very easy to see the spread. The disadvantages here are a little bit, I don't want to say off, but it's less compact. I mean, I don't really know how else to word it. When you're dealing with a large cell or a matrix, you can't reduce this value down. When you are dealing with vector data, it's very easy to reduce lines and polygons down to their original points, and then just basically write a rule into the code saying you will start at point X, and then you will go all the way until the point is closed, or until X is meeting this in the most direct fashion, or however you want it done. You can't do that with raster data because it's best showing field data, right? That continuous change in data sets, and so it's very hard to reduce it down further. It also makes topological data relationships very difficult. So when you're showing an area or you're showing different relationships between bodies of water, you're actually going to only be showing one attribute, and the relationship between features within a GIS may actually be a little bit more complex than a single attribute, or the elevation or whatever attribute they're trying to show, it may not present the whole story. And then the final issue is that the output is, less aesthetically pleasing. I mean, that's a good way of basically saying it's not pretty. If you go back 2 slides, you will see the data models, which is the heat map, the subcatchment, and the LiDAR data. It's not good looking. I mean, personally, I think the water basin or the subcatchment is kind of pretty. I think it kind of looks like veins across the landscape, and it kind of shows the lifeblood or whatever of an environment. But it itself, as raster data, does not actually show the attribute well. It shows a nice spread, but it doesn't show what you're looking at well to the human eye. And so it usually requires extensive explanation or extensive external assistance, basically, is the best way to say it, to basically explain what the raster data set is showing, whereas vector data is a little bit easier. When we're looking at vector data, the advantages are kind of the opposite, right? So it's compact. It's very easy to shrink a vector file down. If you have lines, right, or you have polygons, all you need are those points and a direction of how you connect those points into making a polygon. And more often than not, there is an inherent set of rules within the code of a GIS to explain how those files need to connect points. Usually it is in a clockwise direction. You don't need to know that, but it's just a little tidbit of information for you. So when a GIS saves a point class that is going to later be taken and created into a polygon, it is going to save the top point, and then it is going to go to the right and take it in a clockwise fashion until it has the total polygon connected. It's efficient in coding topology. What that really means is that, if you're drawing polygons, it's pretty easy to see the relationship between polygons, points, and lines. And the output is pretty approximate, or it looks about the same as a hand-drawn map. I really don't know how else to say it. Vector data is lines, it's points, and it's shapes. That's what we draw when we're drawing a map. So it looks very similar, and it's very easily to be understood by a layman. The disadvantages of vector is that it's very complex. So when you are actually coding vector data, the relationship between points, lines, and polygons becomes very difficult, especially when you're working with multiple types of data, which makes these overlay operations very difficult to implement. Thankfully, we're using ArcMap for this class, and so much of this is not something you have to worry about, but it's important to know what your data represents and how it is represented, because vector and raster don't speak to each other unless you make conversions between them. And it's something to consider when you start really layering multiple pieces of data together onto a single map, that not everything talks together. And so when you try to perform a function or a measurement or some sort of analysis, it becomes very hard to see what you're looking at, or it becomes very hard to understand what the output is and what has been included and what hasn't. So let's move out of the models. Hopefully I have explained this well enough. I know it's kind of a confusing thing to think about, especially for anyone that has never really had any time to either think about how data is represented within a computer program, or how you represent large quantities of geographic data. So moving on, we're going to get into the data structures of today, and this is the second part of the lecture today. So GIS structures, like I said before, right, there's worldviews, which include both the object and the field, and then that includes within that like structure, you also have the types of models, right, vector, and raster. And there are really two types of structures. There's non-topological and there's topological, right? So non-topological does not contain the relationship between pieces of geographic information data, whereas topological does contain the relationship between. And there's also things known as run length and quad trees. So run length is essentially what you would consider for raster data, and quad trees is the way of reducing the resolution within a raster data set. I'll kind of get into that a little bit more, but this is kind of what we're looking at when we're looking at data structures, right? So with raster data structures, there's two things you really have to consider. It's the run length and the quad trees. Run length is essentially how far an attribute will go that has the same value. I have a graph later on to show what that means. And then quad trees is what it is really what it sounds like. If you divide a cell in four, and they're all the same value, you can then shrink those cells down to another layer, and until you get to an area in which not all four values are the same, not all values of the four cells are the same, you can continue to shrink it. Once you reach an area in which all of those values are different, or at least one of them is different, you can no longer shrink that cell down. And then obviously with vector data, it's this, we're talking about this non-topological and topological structure. So the consideration of, is there a relationship here, or is there not, or does it even matter? So when we're looking at raster data structures, data is recorded in order of attribute 1 and the number of cells in that run, and then attribute 2 and the number of cells in that run. And when I say attribute 1 and attribute 2, I don't mean multiple attributes. I simply mean the value of that attribute and the number of cells that are the continuous value. So this is really a better example. I just want to have it all spelled out before we looked at this graph, because once you see this graph, it becomes very simple to like kind of pass over, and the importance is kind of lost on it. So if you're looking here, you see 11, 4, right? So attribute 1 is 11, and there are 4 cells in that run. The same with attribute 3, and there's 4 in that cell, and you can keep going down. But let's take a look at the 5th row, right? So it becomes 11, 3. So there's 3 cells with an attribute of 11. There's 3, 1, right? 1 cell with a value of 3, and 5, 4. A value of 5 for 4 cells. And it continues on like that. So 2 and 6, all the way down to the rest. That's what we're talking about when we're talking about run length. So quad trees are subdividing a region into quadrants until each quadrant contains only one class variable resolution. That's so much better said than how I tried to explain it earlier. As you can tell, that was taken directly from the textbook, but I didn't want to copy it exactly. So what does that mean? The best example here is on the right. This is what quad tree looks like. On the left, you have a vector polygon, right? It's an outline here, and you can see that same structure created into raster data set on the right. The value of those cells depends on the attribute. If the cell can be reduced down into 4 smaller cells, and hold the same level, the same value for the attribute, it can be further reduced. Once you get to an area in which all 4 of those cells no longer hold the same value, you can't reduce any further. I hope that makes sense. I know there's going to be questions here when we start getting into the labs with roster cells. I will hopefully be able to answer more questions. It sounds very complicated, at least it does coming from my mouth. Maybe it's not as complicated for some of you, but it's actually not. It's a very simple process, and it actually makes a lot of sense of why you would only be able to reduce into 4s, right? You have an even value. It creates a consistent reduction in cell size. If you have any questions, you can always reach out to me and I will answer any questions you have. So let's continue on with these graphs. This is one of the best graphs for quad trees I've ever seen. I pulled this again from my mentor from the University at Buffalo. So if you look on the far right, you have the value of the attributes into a code, right? So quad tree 0 is industrial, 1 is industrial, right? So you can see the plain English on the left, and you can see the quad tree on the code in the center. And essentially what this is doing, right, is that you're reducing the size and you're getting the actual value of each cell. So it ends up being things that are, while everything is industrial, it actually is a little bit more important than just industrial, right? There may be industrial, there could be some residential area, and that all kind of spans off further and further. The bottom graph here is it's a tree, right? It's basically the tree that explains how these cells are being further reduced into their own unique subcategories. Okay, so vector data structure is the non-topological, so the non-comparison. Polygons are the basis. One polygon at a time, the data structure records the coordinates of the outline of the polygon. So essentially it considers the shape as the base and the coordinates of the outline are considered. There is no topology and the shared boundaries are recorded twice. So what that means is that when you have multiple polygons within a data set, if there are shared boundaries, those boundaries are then recorded twice. It also means that it ends up recording something twice, and therefore you don't know the relationship between it in terms of data structure, and 2, you're taking up more computer memory. So storing polygons of 2 polygons, 1 and 2, you have the line that is taken from A and B. It's recorded twice, right? So polygon is actually x1, y1, x2 at y2 and on, and that creates polygon 1. The same with polygon 2, but you end up having the same value recorded twice within this structure, right? So I believe it's it's x2, y2, and x1, y1. That line is recorded twice for the same or for 2 different polygons. So when you have a topological data structure, lines are the basis of this this data model. Polygons and nodes are defined by lines, and no lines are duplicated. So in other words, you've reduced the size needed to record this information, and lines and nodes can be referenced to more than one polygon. In other words, you can use these lines and nodes in multiple structures, and all polygons have their own unique identifiers. So if we can refer back to the example from earlier in the lecture of the Huck water data set, if you see that FID, there's going to be a unique identification number to every polygon. And then there are island and whole polygons can be uniquely represented. And what that means is that if they exist on their own or if they exist within multiple relationships of polygon, they also can be uniquely represented. So if it requires just something slightly different than being a relationship in between them. So to use the same example from the non-topological structure of 2 different polygons, where you used to record each polygon as a unique location, and if they overlapped, the overlap would be recorded twice. In this case, you actually only record each line once, and it reduces the total amount of computer memory needed to store the file. And it also allows you to do some sort of analysis, however you want to do. It allows you to do something in between to understand the relationship between both polygons. So something I hope was already broken up earlier, but just to make sure that we're seeing it in terms of like a GIS structure here. A polygon is a list of lines. A line is a set of coordinates, and a point is a line with no length, right? So it's a location, and there's also a second location that has the same value. As you can see from this, there are multiple polylines that are created from multiple points, and they basically span the length between the two. So the final example of topological data structure within a vector data set is the arc node model. And that basically is an arc is a line with a starting and end point at a node. And then the node is an intersection point between two or more arcs, or it's a dead end. And then the polygon is a closed chain of arcs. What this means in its basic core sense is the same thing as what you've been considering for points, lines, and polygons. But it's important to note that there is no there's nothing that exists outside of this, and it's the baseline of structure and a lot of these analytical methods that go within vector data. So within this model, there's the arc coordinate data set, which is the location of these arcs, the polygon topology table, the node topology, and the arc topology. And so it's the relationship of all of these that are all contained within a single file. What this looks like inside of a representation, because it's really not how a computer sees it, but it's how we would see it if we were to go into the files, right? So on the top, you have the digital map, right? And so you have these large black dots, which are your nodes, and they're all connected, whereas lines are the connection between them. And if there's a change in direction, you can kind of change that depending on those smaller points that have no actual value. The nodes are the connection between multiple lines, and the polygon is the closed connection of multiple lines. So you have here you have the breakdown, right? You have the polygon topology, the node topology, and the link topology, and it's basically showing the coordinates between them. And then the link coordinates on it sits itself on its own to explain the coordinates of each line. So it's a breakdown of all of it. Okay, so that is essentially lecture 3 of many lectures, I guess. So that's chapter 3. With the next lecture we have, which is going to be data structures, I believe. Hold on, let me check. It is going to be databases. So we're going to go further into the explanation of databases. For many of you, I know that this is just an introduction and you have no desire to continue on within GIS. And so really you only need a baseline understanding of what we're talking about here. It is important to have some understanding of the differences between vector and raster data sets. It is not important that you know all of the breakdown of how everything is structured within a data set. However, it's important that we review it, so if you ever have to do some sort of analysis in which you're kind of getting into the fundamentals of how your data is structured, it's important that you know, oh yeah, I think this is something I was discussing with my professor at some time. It's not something you have to memorize. The same thing with the next lecture on databases. Something I'm probably going to keep saying, databases are really just a fancy way of explaining something that is really more or less going to be held in a matrix of some sort, because computers do not see these wonderful graphical user interfaces. They don't see the YouTube interface that you're watching this video on. To them, it is just a bunch of binary ones and zeros that have been converted through multiple languages to be read and written by human beings. The same works here for raster data set, vector data set. It's all just a bunch of binary ones and zeros that are shown through connection, really in a graphical user interface that for us is going to be ArcMap. It is important that you understand that these are not just lines or they're not just cells that you can see, though. that there is a relationship and how they are ordered has a reason.